Now, here's a topic I find really fascinating: island biogeography. Let's get on it. First of all, I love islands. I don't know about you, but I just love islands. I don't care if they're tropical islands, I don't care if they're little islands, big islands. I just think islands are really awesome. And it turns out they're a very interesting laboratory with which we can study things like speciation, extinction, biodiversity, and so on. So, island biogeography basically it describes the dynamics of small isolated populations on islands. But although we're going to focus on islands specifically, like what you would think, like in the ocean, um, you can use the term to study any small isolated population. So we could talk about, say, a small forest area that's like a land preserve that's urbanized around it, or we could talk about a mountain that has a different habitat on it compared to everything else around it. So anytime we have a small ecosystem that's separate from everything else, we're talking island biogeography. So let's look at what some of the ideas here are. Okay, so the idea is that the biodiversity of isolated systems depends on basically two things. It depends on the rate at which the island becomes colonized by new species and the rate at which species go extinct. Now, when we talk about going extinct in island biogeography, we're not talking about going extinct as in that species doesn't exist anymore, like the dinosaurs. We just mean it doesn't exist on that island anymore. And sometimes it will exist on an island for a while and then it will leave. For instance, like say a human shows up from the Titanic, right? Or Amelia Earhart crashes an airplane. So there's one, human on that planet for a few years, and then that human leaves. That humans went extinct on the island, but they might come back. So another plane might crash, another person might show up. So the idea is when we talk about the extinction on an island, we have to understand it's a dynamic situation. Species come, species go, but at any point in time, what we find is what really matters is how big is the island and how isolated is the island. These are the two factors that determine the richness of species that we're going to find on the island. So islands, how do they form? Well, for the most part, they form as a result of volcanic activity. So, like you're familiar with the islands of Hawaii, those are just volcanoes. The big island is the active volcano we see with Mauna Loa and Kilauea. We see that, right? But directly offshore, underwater, there is another volcano coming up. It hasn't reached the surface yet, so it doesn't have anything living on it, at least not no terrestrial organisms. But eventually, it's going to breach the surface of the ocean, and we're just going to have this raw volcanic rock. But over time, life is going to find a way to colonize it. Organisms are going to immigrate to this island. Now we're talking, terrestrial and avian, flying organisms and things that come over they raft over on debris, whatever. But basically, life is going to find a way to this island, and it's going to take up residence. So that we call it colonization or immigration, and that's that's really what we're focusing on in island biogeography is how rapidly do organisms arrive at the island and how likely are they to survive when they get there. So again, the two main factors to think about are the size of the island and how isolated it is, how far from the mainland. So I just went to Google Earth and pulled up these. So if you look here, we've got like this Isla, I'm how hard to say it, Gobernadora. It's a fairly large sized island, but it's also very close to the mainland. As a result, we would expect to find quite a bit of biodiversity on this island. If we look here, we have a little tiny one, and it's far, far away from the mainland. In this case, we would expect to find very low biodiversity on this island. Now, here we have one that's very large, which makes it likely to have a lot of species, but it's still fairly isolated. So those two factors, how far are you from the mainland and how big are you? Those are the two things that really come into play in determining how many species we expect to find on an island. So let's start off with distance. Clearly, the farther you are from the mainland, the fewer species that are going to reach you. How they get there, like, well, flying ones fly. A lot of plants basically drift over. There'll be a storm that will just wash plants off the shore, and some of them will end up making it to the shores of the island and take up residence. A lot of times, small things like insects might blow over with the wind. Some larger ones raft over with the plant matter. Some of them get introduced, but we're not really going to focus on that. So the idea is that the farther you are from the mainland, the less likely it is that organisms will find the island and therefore will expect to have less richness. So we see here is here's the number of species on the Andean Sky Islands, and what we see is ones that are close to the shore have between say 35 and 50 species. But as we move farther and farther away and get close to like 450 kilometers offshore, the number drops considerably. And notice it's not a law of nature. We do have some variation here, but there's a general trend that we notice. The farther away you are, the less likely you are to be found, and so the lower number of species are going to be present. That's not hard to wrap your head around. This next one, we got to apply some of what we know about ecology to understand this. Okay, specifically, everything in terms of uh, competitive exclusion. So now, if we talk about the area of the island, what we find is this. Look at this graph here. What this is showing us is the number of species goes up. Uh, yeah, this is the southwestern Sky Islands with the amount of area of land. Now, if you look here, this is a logarithmic scale. It's still trying to show, though, that there is this trend of a greater amount of area equals a greater number of species. And the reason that would be is that once you arrive, if there's more area, there's probably going to be more different niches that can be filled. There's going to be less pressure for competition, and therefore species will be able to survive, even if they have to resort to partitioning of resources. They have the opportunity to do that. There's not this hyper competitive environment that you would have in a very small island. Now, I just want to take a quick look and see, like, if we don't scale this way, what does it look like? It's pretty remarkable. It's this beautiful square root curve, all right? So basically, now this is in square meters, but you see that the number of species goes up with area. That's the main thing we need to know here. So again, so the idea is if an island is small, there's a good chance that a species upon arriving is going to go extinct. And that's going to happen for a couple of reasons. One is if it's a small island, there can't be a very large population. So what happens is if you have fewer breeding pairs, you have a small population, well, if something happens like a storm, you can just wipe them all out. Or if there's a disease, a small number of organisms means you have a smaller genetic variety there. There's less genetic biodiversity within the species. And so there's a greater opportunity for extinction to occur. Also, competitive exclusion says, well, if you've got a small island, there's going to be a lot of competition, and the species that arrive are going to get out competed before they have a chance to find a sub niche to move into. So, bottom line: small area, more extinction, fewer species. So let's look at these graphs here. We got to be careful here. These take a little bit of time to wrap your head around. So here's the idea. This y-axis is the rate, and we're going to show the rate of two things. The blue line is going to be rate at which new species arrive, not individuals, new species. So if one turtle arrives and then a while later another turtle arrives, well, that's the same species. That's not on this graph. This is just how many new species arrive. And the x-axis is the number of different species that are already on the island. So if you think about this, at first, the rate has to be high because there aren't any species on there. So everyone who arrives is a new species. So of course it's going to be high, and there's less competition. But with each new arrival, there's more species on the island, and the odds of a species being a new species is pretty small. So we always get this curve from high down to zero like this. Now let's compare a far island to a near island. We're going to get the same curve, but what's going to happen? We're assuming the same size island. What happens is that near island, the rate of arrival is going to be much greater because it's not that hard to get to. The farther island is going to see the same curve, but it's going to happen slower because the rate is less because it's harder to get there. But eventually what we find is when a species arrives, that species is already there, so it can't make room for itself. Now let's talk about the extinction rate. So the extinction rate would go up with the number of species. Why is that? Well, more species means more niches filled. And so when a species arrive, if those niches are filled, if a new species arrives, but it needs a niche that's already filled, chances are it's not going to survive. Now, it is possible that it could outcompete one that's already there, but the odds are against it. So the general trend that's been established is the more species you have on the island, the higher the extinction rate is going to be. There's more species, well, more of them are going to go extinct. And then if we compare a small island to a large island, what we find is on a large island, that rate of extinction is a lot smaller. There's more niches, there's less competition. On a small island, it's the opposite. Fewer niches, more competition, more extinction, or like a higher rate of extinction. So now let's combine these two graphs to figure out how many species would we expect to find on an island. We rely on an idea called the equilibrium point. So the idea is where these two curves cross each other, that's how many species we'd expect to find on our island. So basically, remember, this is the rate at which new species arrive. This is the rate at which species go extinct. And where these two lines meet, that's how many species we'd expect to find on the island. Now let's compare a near island to a far island. We said that we would expect to find a greater number of species, higher biodiversity on near islands. Here's why. On a near island, the rate of arrival is higher, but the island is the same size, regardless of whether it's near or far. We're assuming the same size island, and as a result, the extinction rate is the same. So we find as for the near island, the equilibrium point is here, giving me a large number of species, and on a far island, the equilibrium point is here, giving me a fewer number of species on the island. If I was to increase the size of the island, what would happen is this line would drop down, and I'd still have more on the near island than the far island, but I'd have more of them. See, I told you it's kind of cool. I like this subject. Okay, what am I showing here? I don't know because I didn't label. I think I'm going to show you a different sized island. A larger island. I knew it. There, that's what I was talking about that last slide. So what we see is, I didn't label this though. Let's just think about this though. This one here has a higher rate of extinction, so that is a small island, and I have fewer species. The lower rate of extinction is what I expect on a larger island, and so I'd have more species. Eric, I can't believe you didn't. I'll label it before I put it in the folder with all the presentations. So if you go back and look at it later, it'll be labeled. Sorry about that. So let's just try one more time. Here we're keeping the distance constant, so the rate of arrival stays the same. But on a smaller island, we're going to have a higher rate of extinction and therefore fewer species. And on a larger island, I'm going to have a lower rate of extinction, so therefore a greater number of species. Now let's just take a look at a couple of real-world examples here. So here off the coast of California, we have what are these called? These are the Channel Islands. My son was just there the other day. He went out to one of these islands. Okay, so here's what you got. You have these four islands in particular. So let's just look here. Let's look at the one we think we should have the most. It would be this one. Santa Cruz Island is really large, and it's a bit closer than the only one that's a little bit closer is Anacapa Island. But you notice that this one has the most bird species on it because it's pretty large and it's closer than the other ones. If we look at Santa Rosa, it's about similar in size, maybe a little bit smaller, but it's definitely a little bit farther from the mainland, and as a consequence, we have fewer species. If we look at San Miguel, it has the fewest. It's not the smallest island, but it's pretty small, and it's also pretty far, so it has the fewest. And then Anacapa is a very small island, but it's also very close to the mainland, so the rate at which new arrivals reach it is higher. So let's just recap this. Ready? Okay, and then we'll be done. A large distance from the mainland means less species because fewer species arrive. The rate at which they arrive is less, so you're going to have less on the island. A large area means there's more room, so you're going to have more species. There's more niches to fill. Populations can be larger, which makes them more stable and less likely to go extinct. If you have a small area, you're going to have more extinction. There's more competition. There's fewer niches. The populations aren't as big. They're not as robust. They don't have as much genetic diversity, so they're going to go extinct more. Remember, that's just extinct on the island, not in the world. But now here's something that's going to be interesting for a subsequent lesson, and that is that a small area would also mean, in addition to greater rate of extinction, a greater rate of speciation. New species will pop up on islands at a much greater rate than they do everywhere else, and that's because you have a smaller gene pool, and therefore you can get genetic drift that leads to new species much more easily on these small islands than you can on larger ones. So what we find is islands tend to be places where we find a lot of unique, or rather what we call endemic species. Okay, and here's what you can read in your